into three categories, where 70,000 will be regular customer, 20,000 premium, and 10,000 as a VIP customer. And we are creating population spending data set. So here we are creating the population spending data set. And here, then we are saving the data set into CSV. Similarly, we are creating AB data set. Similarly, here we are creating uh, two two category of website data set, where AB testing is for testing uh, which is more effective. So what we do is, to one sample we provide design A, and to the second sample we provide the second website, and we see the conversion, that how much time the website user is staying, or the link user is clicking. So here, conversion and time. Here we are generating two data for two website, and then again we are saving it in the data CSV data, and then employee satisfaction score. Similarly, we are creating 500 sample data. Here we are creating, just a second. Okay, so here, so we are creating a satisfaction score of 500 employees, where we are generating random employee ID, department, and we are making a random choice for the department among these: sales, engineering, marketing, and HR. We have already covered all the NumPy random data generation. So using those things, we are generating the sample data frame, year, experience, and satisfaction score. So here we are going to use these three data set in our today's session. So when this code is run, you will see that three CSV file got created: one for population spending, A/B test, and employee satisfaction. So let's get started with the foundation. So let's understand the population versus sample. So whenever we deal with the statistics, you always will hear the term called population versus sample. So the population is the complete group you want to understand. So the population, for example, uh, let's say when a voting happens, the overall people who casted their vote will be considered as population. And for the survey, when group of people were interviewed after when they casted their vote by the news channel, are called as sample. Similarly, let's say there might be lakhs of customer for a website, for a e-commerce platform, but it is not possible for the e-commerce platform to conduct survey for all these customers. They can't call everyone and ask a certain survey question. So they select the some sample customer from their population data set, and they do the survey. So from this, you can understand that the population is overall group, the complete group, and sample is the subset that you observe. That is the data in your hand. So let's see. So population versus sample, and this is the foundation of statistical inference. So the population is a complete group you want to understand. Let's say n equals to 1 lakh customer. So you can't survey all the customer. So you take a random selection and select a group of 30 customer. So that is the difference between population versus sample. So here, let's say, so what we'll do, we will load the data set, our population spending.csv, and we will get the spending data from that data frame. So if you look at the generated data, so here, the data, what we generated, consists of only spending, and each spending represent individual customer spending, unique customer spending, only that data is present. So we are selecting the spending. And so now this whole data set will represent population. And here, sample, for example, um, here using the NumPy, we are randomly selecting, but in practical scenario, you will also do a random selection from your customer database of customer, and then you can go ahead and ask the survey. You can do the survey, for example, or if you want to do any statistical analysis, you will do a random choice, and then that will be considered as your sample. Here we are choosing 100, sample size of 100 from the population. So here, total customer are 1 lakh, and true average spending is $95, and the true standard deviation is 91. So I hope you understand what standard deviation is. Standard deviation tell us how clustered the data points at the mean. Higher the standard deviation, higher the variance. That is the difference from the mean versus the other data point is high. So you will get the higher standard deviation. And so that means you can say that the range is higher. Low, between the data point, you will get the lower standard deviation. So this is on the overall population. And in reality, it is next to impossible to carry the statistical summary on population because in most cases it is impractical and very costly and time consuming thing. Let's say, for example, uh, if you want, let's say in an office, um, cafeteria, and they are going to increase the price, let's say, and let's say how much people are comfortable in paying extra by percent in terms of percentage. Let's say a simple survey needs to be conducted. So it is very impractical that if they survey each and every employee, so what they can do is they can select 50 or maybe 80 different employees, and they can survey and get the idea like how much comfortable the people are in paying extra due to the inflation. So that's the reason why whenever we deal with the statistical analysis, we deal with the sample, because in most of the cases, considering all the data point of the population is in most cases is not practical. So now when we do the sample summary, statistical summary on sample of 100 size, what we see is, for example, sample average is around $85. So it is a fact that whenever you do a sample average there, it won't represent a true population average. It will be different. And when you do, and when you keep on repeating the average, you will, if you keep on taking the sample and if you take its average, and then if you plot it, then you will get the normal distribution for the sample average. We'll look it on later on. But from this, you can get the idea that what the true population represent, the sample might not accurately describe it, but it gives a brief idea. And you can see the standard deviation for the sample is around 88, 91. So the sample average is close to the population average, but not exactly the same. So this is the thing we have to always consider. So, so now let's come to the so parameter versus statistic. So parameter describes the population and is usually unknown, because we have already discussed that collecting all the data point for population is next to impossible. Just hold on a second. So yes, so parameter describes the population and is usually unknown and has a fixed value. Because why? Because you won't get different result, because population is going to be a fixed, because it covers all the data points. So whatever the statistical summary you derive will be always a fixed value. Okay, and the statistics, when we deals with we generally deals with the sample, and it describes describes the sample. Calculated from the data varies from sample to sample. As you can see in our code, that for this particular sample, randomly chosen sample, the average was 85. But if you would have taken another, let's say if I change the seed here, instead of 128, let's say if I make it 125, and let's see here, you can see that now the sample and the sample size is same, but now the sample average has changed because of the now the sample is chosen in another random order. So this suggests that your statistical summary or statistic varies from sample to sample, and the notions notions used to represent the parameter mu, alpha, and so on. And similarly for X bar, S, R, and R are used for the statistics. So the key insight is that we almost never have access to the full population. And the statistical inference let us make educated guess about the population using only a sample. So the goal of statistical inference is to make a educated guess about the population. So we have, when we get the sample data, our goal is to get the clear idea about the population, not about the sample, of course. So we have also seen that different sample will lead to different sample mean, slightly different answer. So every sam here, every sample will give you, whenever you take a sample from the population, and when you get the its statistical summary, you will get slightly different answer, not only with average, but also with your standard deviation, variance, or any statistical statistic, you will get the different answer. So now the central limit theorem. This is the most important theorem in statistics, and the whole statistics is practical because of this theorem. So what does central limit theorem says? So the central limit theorem says that, so for example, this is our customer. This is, let's say, in reality, we won't be having uh, the overall population data. Even if in the case of e-commerce, you will say that we, of course, we have the complete overall customer data and we know the current spending behavior. But this is not a fact, because we are not considering those customers, those who will be spending in future, or those who will join the platform in future, right? So this is not the complete customer. Future people, in future also, the other people are going to join the part of e-commerce. So that's why, even if in a close uh, e-commerce platform, you won't say that the customer database what we have is a complete population, because there are still customer outside the e-commerce platform, those who can become the customer in future. So but in reality, let's say if we have this kind of data set for the population, and where the customer spending is like this. So this is definitely not normal. This is not and this is not normal, and this is right skewed. You can see the tail is getting stretched on the right side. So uh, here, the maximum customer is over here, around uh, around 70,000, for example. So this is 70,000, around 75,000. And here 0.5 means 50,000, and 1 means 1 lakh. So here 70,000 around customer are in the range of under maybe 10 $10 spending. So, and very few customer are in the range of $300 spending. So let's say this is a kind of data what we have about the population. And now this is the, let's say, distribution of sample mean now. But if we collect the sample, so this in the previous case was kind of a real picture. This was the real picture. And if you collect this sample, let's say here, it won't uh, it won't represent the uh, a real kind of distribution.
So this is a skewed metric, slightly skewed.
Sorry.
Is it rightly skewed
Yes,
metric?
this is right skewed, because if you look at here, yellow dot represents mean, and on the right side, it is still getting skewed. It is still skewed. Yes, you are right. And one more thing, this is a distribution of sample mean. Here, uh, we have taken, here we are taken an sample as 5. And sorry. So here, as we keep on increasing the sample, as we get more sample, you can see that it is getting more and more beautiful bell curve. And here, when I am taking a sample as in number of sample, not the uh, okay, let me get this thing clear, what's happening in here. So let me see if this code demonstrates that. Okay, so here, uh, okay, so here what exactly what we are going to do is, in the first, definitely we plotted the, this is for the population, and the population mean is around 95. And here, now what we are going to do is, in the Okay, in the plot 2, what we are going to do is we are going to, so here we have created a function called simulate sample means.
So if we take different sample size, na,
Yes,
for
so
the
yes, so basically here what we are doing is we are uh, taking not we are not changing the size of the sample, but changing the number of sample. So here, so for example, if you look at here, uh, so here we are here the parameter number of sample is 1000. So we are taking 1000 individual data point. Okay, and here
sample
samples.
samples.
uh, Number
Uh,
of sample here means the number of data points. Okay, and sample size means the number of time we conducted, let's say number of surveys. So let me visualize you in this way. So for example, let's say you have to do a customer survey and you decided to conduct, let's say 30 times you want to conduct a survey, and in each survey you take 1000 sample, let's say 1000 people. So here sample size is the number of time you did the survey, and number of sample is in individual survey how many people you involved in.
so basically that means the population size is 1,000 and we take around 30 people
No,
out
no,
of the subset
population
of,
is one, population over here is 1 lakh. Population is 1 lakh, and from
and
1 lakh, you, let's say you do the first survey, you take 1000 sample,
okay,
you one sample 1000 people, as in 1000
okay,
data point in the
yeah,
first iteration, and that becomes your first sample, and here you do it for 30 times. So that means that in the first you conduct it, you take the 1000 people, you conduct the survey, then you do it for the second time, you again collect different 1000 person, you collect the data, and you do it for the 30 times.
got it.
Okay, so this is what sample size means, and number of sample in the particular, in the particular your sample collection.
So basically we did that because we find out to the normalization of the curve. That's why we are taking the different number of people and different number of sets.
Exactly, you are right. So here the central limit theorem says that if you keep on increasing the sample size, not number of sample, you have to keep it optimal, but it shouldn't be that much high. It doesn't need to be, number of sample shouldn't be that much high, but if you keep on increasing the sample size as in, if you keep on increasing the batches of the survey, it will start forming a normal distribution. So here, when n equals to 15 and n equals to, here, when n equals to 5, it is said that it was the number of time the sample was collected. Okay, here each, let's say for the, here 5 times the sample was collected for here, what, let's say 30 data points. Okay, and then its mean was conducted. And as you keep on increasing the number of time you conduct the survey or collection of sample, are you getting, not the data point collection, but the number of time you conduct the survey or process of collecting the sample? Are you getting, are you clear about this? There is a there is a difference between number of data point and number of times you collect the data point. Are you still confused, or is it clear, somewhat clear? Okay, let me repeat it again. So let's say if you have, let's say 1 lakh population. So Now you want to find out about the population. So here, in the first case, when we took the samples summary, that is what is its average, every time when you collected the sample average, it was returning a different picture, right? So what the central limit theorem says is, rather than taking the sample mean only one time, if you keep on repeating, so first, let's say this is for the sample of 100. Every time first time you go and select the 100 people, or any from, let's say if it is let's say pollution, it can related be with the earth science, or it can be related to any field. You select 100 data point, you collect the sample, and you record its summary. Then you again go and repeat the process. Definitely you will again get some other sample average. You keep on repeating it. Let's say if you do it for 5 times, and if you do the average of average, it will be somewhat start becoming closer to this. So here, each sample point might not represent your true population, but if you repeat the sample, if you repeat the process of calculating the sample statistics, and if you summarize it, then it will start converging towards the population. That is what central limit theorem is. So, uh, so here, and it is said that if you repeat the sample collection process for n equals to 30, that is, you collect the sample 30 times, then it will converge, it will come closer to your, much closer to your population average. Definitely, if you go higher, then also it will be definitely much more closer to the population, but it again is not practical due to the cost and the time and the practicality of data collection. So, so here you can see that as you keep on increasing the number of if you keep on if you increase the sample collection process, it it tends to form a normal distribution, and it here n equals to 100. You can see that data is properly mean is around the center, and properly it is not skewed either right or left. It is centrally aligned data. So this is what central limit theorem says, that if you, rather than collecting only one sample of n sample size, num you conduct around 30 survey or 30 batches of sample collections, and then you run your statistics on that. So this is what your central limit theorem says. So here you can see that um, so as you keep on increasing this number of sample process, here your standard deviation keep on decreasing.
Sir,
Hmm.
So am I audible?
Yes, you are audible. Yes.
Sir, my name is Akshay. Basically, you told that for n equals to 30, the sample basically will be normally distributed, isn't it?
Sample, not the sample. If you run the statistical summary on the sample, so uh, here what this data represent is for the, let's say, for the first sample, here let's say, if you let's say here this is the true spending of your population. Here each yeah, over here, let's say this is around, let's say, around $10, and $10 is the at max, and it goes till 400. So this is kind of true spending. And here, this is the samples average. So what you do is you collect, let's say, 100 data point from the population. For five, here it's if n is 5, if this is n is 10. So here you collect 1,000 samples 10 times. You calculate its mean for each and every time, and then it gives you a kind of sample of mean like this. And if you keep on increasing n, that is number of times you collected the sample, it tends to become normal. What is becoming normal? The average of the sample,
Basically, mean of the sample.
mean of the sample, exactly.
Sir, but while can you scroll down a bit? Here you can see just here.
Uh-huh.
When your number of observations is 30, the standard deviation is around $16. And when you have increased the number of observation to 100, standard deviation is like $9.9. So basically, more the number of samples, more better will be the standard deviation. Then why we are taking only 30 population for CLT application? Why not we
See, basically
increase?
and the reason is, here this is first of all, because of our data, it is showing around 16 and 9. And the second thing is, in reality, conducting 100 rounds of survey is not practical, because each survey cost time, money, and kind of and to get the data point is very hard, right? So the statistics is all about taking optimal practical effort to get the idea about the population. So of course, if you keep on increasing the number of times you collect the sample, if you keep on increasing, it will represent keep it will the accuracy will keep on increasing. That is a true fact. But the thing is, you have to also consider that the price of the sample collection, the time required for the sample collection, the effort required is also very high. So you have to stop. And that's why it is said that when you conduct n equals to 30, this, of course, it doesn't give you a true picture, but it gives you a much more realistic picture compared to n equals to 10 or n equals to 5. If you see the difference between 10 and 30, it is 30 and 16. If you go to 40 or 50, even if you go to 40, it will much it the difference will between 30 and 100 will be much less. If you go to, let's say, you can if you find a pattern that, okay, if you can afford, you can increase n equals to 40. There is no hard and fast rule that you have to stop at n equals to 30. You can go to n equals to 40, but at n equal to 40 will give you much more precise uh, idea in the picture, rather than doing n equals to 100. So if you do n equal to 40, maybe the standard deviation might be around, let's say, dollar 11. And now dollar 11 at n equal to 40, you're getting dollar 11, and you have to invest double or triple amount of time and money to get more precise and clear uh, idea about the population. Are you getting what I'm saying? So basically here, the optimal region is around 30. It is not something hard and fast, but it is around 30. It is considered that you can get the better idea about the population.
Okay,
So
sir.
of course, if you go for n equals to 1000, let's say, then your standard deviation will be not will be, let's say, around $8.5, because if you, because it is something kind of logarithmic curve. So if you keep on increasing the effort, the change will be very negligible.
Okay, sir. Got it.
So now let's try to understand the concept of standard error. So here, the three and in the central limit theorem, when we talk about three properties of central limit theorem, the shape, the shape, when we increase the sample mean, the number of time we collect the sample mean forms a normal distribution regardless of the population shape, right? We saw that in the here, regardless of the population here, because population is about the real data point, real spending, whatever it is. But when we talk about the central limit theorem, number of, when we collect number of times the sample we collect and we plot its average, it always forms the standard distribution, normal distribution, because here we are not plotting the real distribution of sample, but the mean of sample collected. You see the difference, right? So that's the thing. So sample means we are plotting, and we get normal distribution regardless of the population shape. Mean of sample mean, when you increase the n, it becomes closer to the population mean. Spread, larger sample, we saw that it gives the narrower spread. And how that is calculated, we will look into the next thing, the standard error, how it is calculated. So in order to so basically standard error is to determine how accurate our calculation is. So basically, now what is the difference between the standard deviation versus standard error? So standard deviation tell us that how spread our individual data point is. So let's say these are all individual data point. Let's say here, let's say this is the spending, and this is, let's say, number of customer. On the y-axis, the number of customer, and your x-axis is your total amount spending. So here, yellow dot, let's say, represents the average of spending, and individual data point here represent the spending amount, and higher this thing means the number of customer are high in that spending area. So what the standard deviation is? Standard deviation tell us is a measure that tell us that how far individual data point is from the your mean. Okay, and what does the standard error is? Standard error tell us how much the sample mean change with a new sample. So basically, when you collect the first first you take the first sample, you take the average, and then you then collect the second sample, and then you again collect the average. Now the difference tell us the how much mean changes with the new sample. So if the mean is if the change in the between the average, let's say if you collected n equals to let's say you collected the first sample of, let's say 50 customer, and you calculated its average. That was something around, let's say, $20. Then you collected another round of 20 customer. Now its average is around, uh, let's say 25 dollars. So now here with the next batch, you can see that there is a change of in the average there is a change of $5. And now if you increase, if you take one more sample, and if it is between let's say 22, so now if you take the mean of the error, it is now becoming it keeps on decreasing, right? Earlier on it was $5, now it is around if you collect the sample of this average, it is around 22. It is very close. Now error is much less. And if you again take next batch of sample, and if it average around again around 23, so this is way to calculate the standard error. And this tell us, and definitely if you keep on increasing the n, your standard error should keep on decreasing.
Sir,
Yes. Yeah, tell me, go
so
ahead.
sir, basically the meaning of standard error is that if I will add any new sample, how closer I will move towards my original population mean, isn't it?
Yes, you are right. So
Okay, sir.
basically, yes. So basically, as the sample size increases, the standard error decreases. And this is the mathematical reason why larger sample gives the better estimate.
Okay, sir.
And here, the formula for so the formula for uh, so the formula for calculating the standard error is standard deviation by your root of n, and we will look into it how to calculate it. And here n means your number of times you collected the sample. So here so here again we are taking sample uh, of 100 sample of 100 from the population. And here, in order to calculate sample standard deviation, we have to we have to set degree of freedom as DDoF as 1 as the parameter. So in this way, we are able to calculate the standard deviation of the sample. So whatever the sample is, you can using the NumPy method. This is a NumPy method where you have to set whether you are calculating for population or sample, you have to set it. And for setting DDoF equals to 1, it tells the NumPy that you are calculating the standard deviation for the sample data. And then in this case, in this way, you get the sample standard deviation. Sample size you get by directly getting the length, and then simply you have to do the standard deviation divide by square root of sample size. This formula you apply it, and then you get the and then now here we are plotting the how standard error changes with the sample size. Here what we are doing is we are increasing the sample size, and here again, and we are calculating the standard error, and you can see that as the sample size increases, your standard error is also decreasing. And also, as you raised earlier, as one of the student raised earlier, that why to uh, stop at 30 if the accuracy is more in increasing the number of sample or batches of sample. So here, if you look at this thing, that if you keep uh, n equals to 25, so the standard error is around 17. If you keep at 50, it is around 12. But after doubling the sample size, the difference is very negligible. And although yes, converting into from 50 to 200, of course, there is a huge difference, but the cost of increasing the sample size from 50 to 200 is much higher. And if you go to 500, then you will have to do it 10 times more in order to get more precise error. And beyond that, you so here, if you, let's say, if you conduct the sample, if you take the sample size of 500, and for the next 500 the change is negligible, right? So that's why you in order to get a better idea, you can stop at a smaller end. You don't have to go a sample size of 1000 or higher than that. So so that's why it is said that a brief idea can be observed from the sample size of 30. That is not something hard and fast rule. You can increase n equals to 50, n equals to 100, but the cost involved will also will increase exponentially here, and the accuracy will be logarithmically very thin. The benefit what we get. So
Sir,
yes.
sir, why we have kept a degree of freedom as one in the program that you have shown up?
So basically here, the degree of freedom is a statistical way. So basically here, in order to uh, tell the numpy that we have to find the standard deviation. So basically, uh, when we don't provide the degree of freedom, it considers the data to be the population, and it in order to calculate the standard deviation, it divides by n. The number of data point is considered as n, the whole thing. And when you want to calculate the standard deviation for sample, you have to divide the it by n minus 1. That's why we have to set degree of freedom as 1. So because it is considered that the sample data is not a complete picture. That's why you have to divide by n minus 1 in order to calculate the this thing standard deviation. So that's why we have to set dd of f equals to 1 to let numpy internally know that you are calculating it for sample, not for the population.
But sir, degree of freedom itself is n minus one in this case, I guess. When I mean, as far as I know, the degree of freedom is itself n minus one rather than being divide. I understood that n minus one is divided because it will be understanding that it is whether a sample or a population.
Right.
But n minus one is basically, I guess, degree of freedom itself.
Yes. So here the thing is that this is an argument. Uh, so if you look at here, it is it tells the numpy that it has to internally calculate n minus 1. So basically, if you look at the, let me see the documentation. Uh, so so here, if you look at the NumPy documentation, and so here zero means your here means delta degree of freedom. The divisor used in calculation is n DDF, where n represents the number of elements. By default DDF is zero. So for population it is zero. And when you set one, so n minus one internally, uh, it will do the n minus capital N. And here your capital N by default is zero, and when you provide one, it will do n minus one. Are you getting? For the population, automatically it consider n as zero. Sorry, minus n, the small n as zero. And here, initially, for the population, if you don't set it, n minus zero will be n. And if you set DDoF as 1, so it will be n minus 1.
Okay, sir. Understood.
So let's move to our next topic, confidence interval. So let's say if company's decision maker asks, what is the average spending of our customer? We could say 87.34, for example. So that is called a point estimate, a single number, a precise. But it is also incomplete because it hides the uncertainty because new customer can join, and at the time of speaking, new purchases might happen. So a better answer might be that it is somewhere between, let's say, $75 and $99, and I am 99% confident about that. So that is an interval estimate. Interval estimate is that you give a range with a confidence about that in percentage. So let's say in an everyday analogy, let's say a point estimate will be that I will be there at 7 p.m. A precise but risky, because there are chances that train might be late or something might happen which might cause a delay. So the better and much accurate thing will be that you can say that I will be there between 6:45 and 7:15. This is called as interval estimate, a less precise but more honest. So here, let's say a point estimate, a single number, 87.34. But if you talk about kind of in terms of confidence interval, you specify your range and with your confident percentage. So the formula for confidence interval is sample mean plus minus Z score, and we will see what Z scores are, and then S by root of n is the standard error. We have already seen how to calculate the standard error. So S by root of n is your standard error. So in order to calculate the confidence interval, you take the sample mean. Z score is calculated based on the accuracy you want. Higher the confidence percentage you want. Let's say you want to be 99% confident, your range will increase. And if you want a range to be very thin, that is, you want your range to be more precise, your confidence percentage will decrease. So Z score, whatever your sample mean is, you add and subtract your Z score into standard error. And Z score into your standard error is called as the margin of error. So in a way, you have to, in order to calculate the confidence interval, you take the sample mean and add and subtract the margin of error. So, so this is the step by step of building a confidence interval. So step one, gather the statistics for n equals to 100. You get the mean, sample mean as 87, standard error as 61.25. Sorry, standard deviation as 61.25. Then you get the standard error. That is the standard deviation divided by the number of sample. You get the standard error. And then you get the Z score. So here, the Z score is a kind of a fixed value. For example, for 95%, it is always going to be 1.96. We will look into that thing, how the Z score and Z score for the percentage gives a kind of a fixed value. It is because of the distribution of normal distribution. We will look into that thing. So everything for a given percentage, confidence percentage, there is a fixed Z score. You get that, and then you take the sample average plus minus the standard deviation, standard error, and the Z score. So that you calculate the margin error, then you add and subtract the margin of error, and then you get the range for the confident, for the 95% confidence. So here we discuss about if there is a precision trade-off. If you want to be high in confidence, definitely your range will increase. If you want to keep your range to minimum, your confidence percentage will decrease. So the good statistical range is for 95%. So here we were discussing about how to calculate the Z score. So for, let's say, when we talk about Z score of 95%, so what does that mean? That 95% of sample mean will fall in this, and then it will be left with 2.5 on the right side and 2.5 on the left side. So here, so that's why 1 minus 0.95. So the sum of this will be your 0.05% or 5%. 2.5 plus 2.5%, 5%, or 0.05 in terms of decimal, and each tail is 0.025. And so the total Z is from here to here. So in order to calculate that, what you do is, middle is 0.95. You add 0.25, that is your left tail, and 0.975, the remaining thing. Sorry, you get 0.975 because of overall 95% of this plus the remaining 0.025. You get total 0.975. So in similar way, you can calculate for the rest of the percentage, for example, 90, and so on. So here, so what exactly 95% confidence really means? So when you take 100 different sample, so definitely it will have 100 different confidence interval. So here you can see that 47 out of 50 interval capture the true mean. So here, this is confidence interval of different sample. Each bar represent confidence interval for different sample. And here you can see that this is the true mean, and here the bar is capturing the true mean. Red one is missing that. So here you can see that because of this confidence interval, what you choose, 47 out of 50 interval captured the true mean. The red one missed. So that means that it is 94% accurate. 94% time it is going to be going to give you accurate sample mean. So here's same thing using code, how we can calculate the confidence interval, lower bound and upper bound. We are doing that. So here we are reading the population, taking the sample, calculating the sample mean, and then we are setting the confidence level we want. And here using NumPy, we are calculating the z-score using this method, where we can pass the 1 plus confidence level divide by 2. This will gives the z-score. For 95%, it will give you 1.96. So rather than hard coding the value, you can use NumPy to get the z-score. And then after the z-score, you calculate the margin of error, that is z-score into the standard error. And the standard error is sample standard deviation divided by square root of n. And then in order to calculate the lower bound of the confidence interval, you subtract the sample mean minus margin of error. And for calculating the upper bound, you add the sample mean and the margin of error. In this way, you get the range, confidence interval range, and for the given confidence percentage. So here, step by step, what we have done, it is shown over here. So in today's session, we learned the basics about population and the sample, and what the CLT theorem says, and about the confidence intervals. In the next session, we will go through the hypothesis testing, and so basically our next goal is to do the hypothesis testing, and we will learn that thing in our next session.
For sure.
Okay, then have a nice week ahead, and bye-bye. And I'll share the code over here, and it will be shared to everyone via email also, whatever we did today. Okay, then bye-bye.
Thank you, sir.
Yep, welcome.